So, the next topic we are going to cover is on vorticity. So, we have already seen what vorticity is. We have already come across the definition of vorticity when we were talking about deformation. We saw that when we are thinking of deformation, the symmetric and the antisymmetric part of the velocity gradient, the antisymmetric part is where we first encountered this quantity called vorticity. Now, just like you can define streamlines, which are lines such that at every point the tangent gives you the velocity vector or the velocity field at that location. You can also similarly define vortex lines, which would be defined in this manner. So, when you had to compute streamlines, you solved an equation based out of this. Similarly, here you will have a very similar equation to solve for, that would be dx by omega x equals dy by omega y dz by omega z. So, vortex lines are going to be lines that tells us that at any point if you draw the tangent to the vortex line, you get the vorticity at that particular point. Now, drawing the analogy from streamlines, in streamlines we know that if I were to use the velocity and compute this quantity u dot dA, I have a small cross sectional area, I find what is u dot dA through that cross sectional area, that gives me my volume flow rate. Integrating this gives me the total volume flow rate through a region. Similarly, here, in order to see how much stuff is going through a region, stuff basically now being in terms of vorticity, we are going to encounter a quantity which is known as circulation. So, circulation is a quantity that is equivalent to how flow rate is for velocity. Here you have a rate for the vorticity, that if you draw these vortex lines, how much of vorticity is basically getting transported through those regions. So, omega dot dA, that is the quantity have a circulation. Now, here we can make this a little bit simpler, because we know there is a relation between velocity and vorticity. Omega is curl of u. So, if I substitute it here as curl of u, so this is over and surface area. So, I have a cross sectional area. The area could be a flat area, it could be a more three-dimensional in shape area, but every area is bounded by a curve. There will be a contour or a curve that is bounding that area. So, if you want a more complicated shape of a surface, imagine that there is a surface like this, which this is the surface, and at the bottom that surface is bounded by that particular curve, the contour. So, if you say that omega dot dA, so there is vorticity vector that is coming out, omega dot dA gives me the circulation, then using the fact that curl of u is my vorticity, I can use Stokes' theorem and transfer this into u dot dl. dl is a line segment that is on the contour C. So, this is a very important quantity in terms of getting a measure for what vorticity is. the circulation that is there in the fluid. Now, we will consider two problems. In the first problem, I will have a velocity u as omega r theta cap. So, what is this? This is a velocity field which, if I draw in 2 dimension, has streamlines that are circular and the fluid velocity goes as omega r. If you are trying to compute what is the angular velocity, the angular velocity in this particular problem is a constant. So, every fluid particle is moving, if omega was positive, in the anticlockwise sense. If you compute the vorticity, take the curl. Now, this is now a curl operation in cylindrical coordinate system. So, in cylindrical coordinate system, this is a 2-dimensional flow. It only has a theta cap component which varies in the r direction. So, this will only have a z. So, I define r theta z as my cylindrical coordinate system. So, omega z, the component of vorticity that is coming out of the plane, is going to be 1 by r dou r of r u theta. There is an additional component of vorticity which is 1 by r dou theta of u r. But there is no radial velocity, there is only an azimuthal velocity. And so, if I now substitute this, I have 1 by r dou r of r omega r as the velocity. So, if you simplify this, dou r of r square omega, omega is a constant. So, I have 2 r omega by r, or omega z is equal to 2 omega. This is what is known as a solid body rotation. As you might have guessed, this is a solid body rotation already from the fact that the angular velocity anywhere in the fluid is a constant. Everything is moving with a constant angular velocity. So, the vorticity here is 2 omega. Now, let us try to compute the circulation. The circulation, if I use omega dot dA definition, I will get an answer which is omega is pointing in the z direction. dA is the surface in this 2D plane, xy plane. So, the normal to that surface is also in the z direction. So, this is basically omega z, z cap dotted with the area vector which is r d theta dr pointing in the z direction. So, you consider a strip, this is of d theta at a distance r, and then you have dr there. So, you will basically compute r d theta dr pointing in the z direction. So, this gives me omega z r d theta dr. So, if you plug your expression for vorticity, you have vorticity is a constant 2 omega r d theta dr. Now, I need to choose a region over which I am doing this calculation. So, let me choose calculating the circulation over a circular patch of radius capital R. So, I choose some circular patch of radius capital R and let us try to calculate the circulation, which means the domain of integration for r will be 0 to r, the domain of integration for theta obviously remains 0 to 2 pi. So, 2 omega is a constant, I pull it outside and then I have 0 to 2 pi d theta, 0 to capital R, r dr. So, 2 omega into 2 pi and then I have r square by 2 capital R which gives me omega to omega pi r square. And this you could have guessed here also, because omega is a constant here. The vorticity is a constant. So, you can take the vorticity outside and just do the integration over the surface area, which is pi r square. So, the circulation is pi r square. Now, would this be the same answer if I were to use the other form of circulation? The other form of circulation says that for the same circle of radius capital R, I will have an integration of u dot dl. Now, what is u? U is omega r theta cap. What is dl? dl would be, on this circuit, it is going to be r d theta, theta cap. And here r also would be, it is evaluated at the radius of a circle of radius r, so it remains the same. So, the velocity at a radius r is omega capital R theta cap, and the line element here is going to be capital R d theta over this small strip. This is the line element. So, if this is d theta, this is capital R d theta, and the direction is along theta cap. So, this is my dl. So, theta cap becomes unity, and then you have omega r square d theta, which gives me 2 omega pi r square. The same answer. There should not have been any surprise, right? I mean, it should be the same answer, because the circulation, this has two ways of defining the circulation, whether you do in terms of vorticity or you do in terms of velocity, they should not disagree. So, we basically have the same answer, you do it either way. We will now consider one more angular velocity profile. This will again be in cylindrical coordinate system. So, u is gamma by 2 pi r. You will see the reason why I am choosing the nature of this particular. Okay, let me just keep it as some constant by r along theta cap. We will find what that constant actually is. So, this is a velocity field which is again azimuthal in nature. By azimuthal, I mean that there is only a component that is along theta cap, there are no other components of velocity field. So, if you compute the vorticity, which is omega z 1 by r dou dou r u theta minus 1 by r dou u r dou theta, this is obviously 0. If you plug it here, I have 1 by r dou dou r of r c by r. R and r cancels out and this becomes 0. So, what you observe here is that vorticity is 0. There is a velocity which is 1 over r, and the vorticity from that is 0. So, now let us go to calculating circulation. So, circulation is omega dot dA, but omega is 0, which means by this definition the circulation should be 0. What about using the other definition of circulation? So, we do the same trick, that it is at a radius of capital R. So, if I plug it in, I have c by r theta cap dotted with capital R. So, this r is going to be capital R d theta, theta cap. So, theta cap dot theta cap is 1, r and r cancels out, and I get an answer which is c d theta or c into 2 pi. Surprisingly, I now got an answer for vorticity, or rather for circulation, that is not 0, whereas from the vorticity we got the answer to be 0. So, something must be going on here which is basically making this inconsistent, and the inconsistency is that the vorticity which we use this relation to calculate, and we plugged u theta as c by r and got it to be 0, it is 0 everywhere other than at r equals 0. So, at r equals 0, the vorticity is not 0, and to be precise, the vorticity is a Dirac delta function. So, it is a vorticity that is present only at a particular location, at a particular point. It is 0 everywhere. Now, if you substitute this, gamma is equal to omega z dA. So, your vorticity is 0 other than at one particular point, and as this area keeps shrinking and shrinking and shrinking and becomes small, it does not matter how small it has become, the delta function is basically going to give you the finite answer. So, you will have here C delta by R and dA is R dr d theta. So, this will then give you a constant d theta delta of R dr, this will be unity and I will have 2 pi c. So, what we see from all of this is if there is a location, so I am drawing now, this is the plane. So, there is a line where the vorticity is infinitely large. This is going to drive a flow everywhere. So, this is driving a flow which is a constant by R theta hat. So, there is a various names for it, a point vortex, a line vortex or an irrotational vortex or a free vortex. The reason why some of these terms are used, point vortex is probably explanatory, that it is defined at a particular point. Irrotational because it is 0 everywhere other than that one particular point. So, you have a location at which the vorticity is non-zero and infinitely large, which drives the flow. This tells you something interesting about vorticity. The relation between vorticity and velocity is the following. You know the velocity at a point, you know gradients of velocity at a point, you can find the vorticity at that particular point. You do not need information of velocity at some other distances. If you know velocity and its derivatives at a given point, you can compute the vorticity at that location. What about inverting this equation? What if I want to actually invert this equation and write the velocity in terms of vorticity? So, if I want to write that what is the velocity in terms of vorticity, this is something which you might have seen already in electromagnetism, where if there is a line of current that will basically drive a magnetic field. So, here you will have over a distance, I am not sure if this is r square, but you will have a relation that will basically give us that the vorticity is going to drive a velocity field everywhere. So, from this particular line, if I draw a distance at some distance r and I want to compute what is the velocity field that it actually drives or what is the velocity field that it is generating, I am going to get over as an integral relation. So, vorticity drives it is a non-local relation, that a vorticity at a particular point drives flow everywhere. So, often that is the reason why a lot of times it is pretty interesting to analyze problems in terms of vorticity, because the velocity field is there everywhere, but that velocity field can have an economical description in terms of the vorticity field. Imagine that your flow is made up of a bunch of point vortices, right. I have drawn here 11 point vortices. You are just tracking 11 objects, but the velocity field that it will generate will be extremely complicated, that it is going to create. So, as these you are tracking only these 11 point vortices. So, your description of motion is only of 11 entities that are moving and interacting with each other, but that will give you a description of what the complete flow field is. So, especially in 2 dimension, studying vorticity is a very economical way of looking at fluid mechanics, that you do not need to look at the entire velocity field everywhere. If the flow field is dictated or dominated by regions of high vorticity, you just track those regions of vorticity and then you will get an understanding of what is going on. Okay. So, we continue with our discussion on vorticity. So, we have come across the fact that the curl of the velocity field gives us the vorticity, and we also encountered a quantity that gives us the flux of vorticity. So, this is defined as omega dot dA, and if I am doing it over a surface, then a closed contour, I could write this as u dot dl. So, that gives me the flux of vorticity through a particular region. Now, the relation for vorticity given a velocity field is straightforward. We have a velocity field, we take gradients and then compute what the vorticity is. For instance, if I am interested in the z component of vorticity, I can just write down the z component of the curl, and it turns out dou v dou x minus dou u dou y, if x, y, z are my components and u, v, w are my velocity components. X, y, z are the coordinates and u, v, w are the components. That is the z component of vorticity. Now, how do we invert the vorticity and get a velocity? So, if you remember from the previous lecture, we went through few examples. So, the example that we had in mind was one scenario where the velocity was omega times r theta hat, and the corresponding vorticity was nothing very complicated. We found the vorticity to be 2 omega in the z hat direction. So, you take the curl and you find that in cylindrical polar coordinate that the vorticity is 2 times omega. But then we also did this problem where we had a velocity field which was also azimuthal in nature. So, it went inversely with the radial distance, and what we obtained there was that if you were to compute the vorticity, we realized that the vorticity is 0 everywhere other than exactly at the origin. So, gamma by 2 pi delta r by r along the z hat direction. So, the question would be that how do I invert given the vorticity to the velocity field? How do I go from an expression of vorticity and find the corresponding velocity field? So, while doing that, if I place a constraint that I am interested in solenoidal velocity fields or incompressible flow field, the approach becomes slightly easier. That saying that the velocity field is already divergence free, I can write the velocity field as a part that is vertical or rotational and a part that is irrotational. Irrotational is something that we have gotten introduced to as something that is having 0 curl. This is definition. Curl of a gradient is always 0. So, I can write a velocity field as a part that has a non-zero curl and a part that has 0 curl. This is just a decomposition of a velocity field. And because this is divergence free, because the velocity field is divergence free, the quantity phi is going to satisfy this equation del square phi equal to 0. This is the consequence of the fact that we are discussing solenoidal velocity field. So, this is something which we are going to do in some detail in few lectures. But right now the goal is different. The goal is how do I find the rotational part of the velocity field. So, the rotational part of the velocity field is related to the vorticity field as, so if I say that I know vorticity over a region, and let us say I am just choosing a line, and I will come back to this description of a line, that I know vorticity at a particular point, what flow does it drive everywhere else? What would be the velocity field that is driven everywhere else due to this particular vorticity field? So, for that we need to know the vorticity field, and let us say I am interested in finding the velocity field at a point x in space. So, this is the point x in space due to the vorticity contribution that I know at a point x prime. So, there is a certain distribution of vorticity, and that distribution of vorticity at a location x prime is going to drive a certain velocity field. So, as you can see, the way we arrived at this particular approach is saying that I know the vorticity at a given location x prime, and then x is where I am finding the velocity field, and this is basically what is giving me my contribution. Now, how do I get this? It's something which is not just randomly pulled out. So, the way to get this is, we said u was uv plus gradient phi, right, and this is divergence free. This object is divergence free, del dot u is equal to 0. So, what I can do, I can write this as curl of a vector potential plus gradient of a scalar potential. So, the idea here basically being that the irrotational part, because if you take a divergence of a curl, that would be 0. So, what you have done, you have basically split the curl and the divergence separately. So, del square phi is equal to 0, that is because divergence of u equal to 0. Now, if you take curl of u, which is my vorticity, so vorticity is curl of u, then I have curl of A plus curl of gradient phi, which is 0. Now, curl of A can be written as del dot A minus del square A. This is a vector identity, that curl of A is gradient divergence of A minus del square A, and A, which is this vector potential, it has this arbitrariness that I can write A as A plus some gradient of scalar and nothing would change, because finally we are to find the velocity field. What are we doing? We are taking the curl of this quantity, right? So, if I say that I have found A, I can find A with an arbitrariness of gradient of a scalar potential. So, there is an A someone has found, and to that I add a gradient of a scalar potential. It is not going to change the velocity field, because curl of a gradient potential is of a scalar potential is 0. So, what we will do, we will use this to actually make that vector potential to also be solenoidal. So, we will choose, this is called fixing the gauge potential. This is quite common in electromagnetism. So, this is saying that you fix a gauge potential, there is an arbitrariness regarding it. So, the gauge potential we are fixing such that this vector potential A remains divergence free. So, summarizing the story now, I have u as written in terms of this decomposition, where the choice is A by definition is divergence free, which means the divergence of u entirely will come from the scalar potential. The advantage then is curl of u, which is the vorticity, is now minus del square A. Now, why are we doing all of this? Because this is a familiar equation. Del square A equal to minus omega, that is known as the Poisson equation. So, just the right hand side equal to 0 would be a Laplace equation. So, we know what are the fundamental solutions of Laplace equation. So, now you can think of vorticity as a source term that is driving this vector potential A, and then you can actually find the velocity, because the velocity is curl of A. So, this is basically the underlying math that goes behind in getting the relation that we are interested in. This is basically what we are interested in, that what is the velocity field given a distribution of vorticity. If I have a certain distribution of vorticity field, what kind of velocity field would be generated due to the distribution of vorticity field? This is an inverse question. Given a velocity field, you can find the vorticity field by finding gradients. But how do you find out the velocity field given that you know information of the vorticity field? So, this is the answer, and the background of arriving at this answer is using this idea that the velocity can be expressed as curl of a vector potential plus gradient of a scalar potential. That vector potential, we fix the gauge by saying it's divergence free. That leads us to a Poisson equation for that vector potential in terms of vorticity. It is like saying that you solve for the temperature field due to some heat source or sink. So, if you have specified the heat source and sink, you can find the temperature field. So, A is a vector quantity. So, the vorticity is like that source or sink. If you know what is a source or sink, you can find that vector potential A. But we are not interested in A. A does not really have a very clear physical meaning. What has a physical meaning is velocity field, which is curl of A. So, this is the path to arriving at this particular solution. So, we are going to focus on this relation, and this is known as the Biot-Savart relation, Biot-Savart law, which gives us the expression for velocity given the vorticity. So, now what I will leave as exercise is in that expression where we had the velocity actually given out. So, in this particular relation, now you can substitute for expressions of vorticity that you are aware of and compute what is the velocity. So, say for instance, you had a vorticity which is gamma by 2 pi delta r by r z hat. So, when you substitute it into this expression, you can see that the Dirac delta function has this very nice property that when integrated over the domain, it will basically pick out a single constant answer. So, you can use that property of the Dirac delta function, and when you do all that, this is again something I am leaving for an exercise, you will eventually find that your velocity field that you obtain would be gamma by 2 pi r theta cap. Few lines of algebra, but you will eventually arrive at this answer which we did in the other direction. We took u is equal to gamma by 2 pi r, and then we got this kind of confusing answer. We got vorticity to be 0, and then using the picture of circulation, we were able to conclude that hang on, the vorticity is not 0, it should have a non-zero value at the origin. And now I am saying that if you take that particular form of vorticity, you can explicitly show that this will drive a velocity field that goes inversely with the radial distance and is purely azimuthal in nature. Okay? Now, this is a vortex line. There is a line where vorticity is present only on the line and it drives a flow. So, the flow is azimuthal, varying in the radial direction, and the vorticity, so this is my r, this is my theta coordinate, and this is my z coordinate, which is why I drew the analogy of a current carrying wire, that the current carrying wire basically inducing a magnetic field. So, you will basically have here that there is a wire, so as to say, which contains vorticity, and that drives a flow, just like it drives a magnetic field in the other problem. So, you have a flow field that is generated everywhere, which are the fluid parcels going in circular tracks, and there is one single location where vorticity is non-zero. Now, the cases which are slightly more complicated from an algebra point of view is, what if instead of it being a straight line, it was a circular line? The line was not a straight wire. So, in the taking the analogy of the current carrying conductor, it was rather a circular closed hoop. Now, this is not something that is unnatural. Having a circuit or a closed loop of vorticity is what appears quite frequently. It's actually probably more easy to see than a vortex line. These are vortex rings, or in some cases when they are visualized using smoke, they will be called as smoke rings. So, a smoke ring or a vortex ring that you will see, or in some cases they are vortex bubbles or toroidal bubbles, where you would have a finite thickness. So, it's basically it has a certain thickness and is shaped like a torus. So, there is a vorticity which is now in the azimuthal direction. So, the vorticity itself is in azimuthal. So, if I draw a coordinate system, a cylindrical coordinate system which is z, r, and then I have theta, then the vorticity here is some constant delta of r minus a theta hat. And you can find out what would the velocity field look like for this given vorticity. Once again, you use the Biot-Savart relation, you work with the integrals, and eventually you are going to find a velocity field that will have a radial and an axial component. So, you would have fluid parcels moving out radially as well as also moving out axially. So, this is a vortex ring which is encountered quite frequently, or rather is not that easy, not that hard to actually observe. So, a line of vorticity that I have said is the idealization. In reality, it would be something that would be more like a tube of vorticity. Now, you can keep thinking about scenarios where you move away from it, and the Biot-Savart relation is what will keep giving you the velocity field. So, if you have a vortex line that is not straight, now what would that do? Again, this is beyond the scope of what we can solve in the class, but you can start to guess what is going on. So, imagine at this particular location there is a vorticity which is, as we said, the vorticity is going to be tangential to the vortex line. So, you have a vortex line that is bent somehow. So, this is going to drive a flow. Now, at this location, which is a little beneath that location that I marked, there is vorticity which is pointing in a completely different direction. Here it is also going to locally drive a flow which is similar to what we see in the picture here. But now there is a difference. The difference is, if I mark these points as, let us say, A and B, the vorticity at A is driving a flow which is going to deform the vortex line at B. Here, if you consider two locations, let us say there was another location slightly above this location. The velocity field, if I mark them as A and B, the velocity field at A is purely tangential. It does not have any component that is radial or axial. So, at B, the line does not have any experience of the velocity field from the vorticity that is there at A. There is no contribution. Whereas, when it is bent, then they can contribute. The moment it is bent in some shape, then the vorticity at one particular location is going to drive a flow that will induce motion in the other location, in the other bent part of that line. So, what this is telling you is that the moment the vortex line basically develops some curvature, it is going to evolve. It is very difficult for it to maintain that particular shape. And it is not just going to evolve, it will also move. There will be some translation, there will be some distortion, and eventually you are going to see that this object can do all kinds of things. It can also like form a loop, and it seems a little too abstract, it seems a little too mathematical, but using these very simple ideas, people have shown that these kinds of loops or knots can form in very large scale vortical flows like tornadoes. So there is a paper by Hassan Aref where he takes this Biot-Savart equation for the connection between velocity and vorticity, takes a filament and basically applies a certain perturbation to that filament, gives some shape to the filament. Eventually, when this grows in a nonlinear manner, the filament will develop these kind of kinks and knots in some ways, and which looks, when you have looked at pictures, there are tornadoes which have those kind of knots, because a tornado at a very basic level is a long vortex filament connected to the ground. So now if you think of that filament actually developing some tortuosity, some curvature, it can evolve in a manner which can at first level be given by this mathematical equation. And interestingly, the circular shape, which is the most bent shape that you have there, is where it doesn't deform any further. So when you have a perfect circular shape, it will not deform, but it is going to translate, which is why when you have a smoke ring or a vortex ring, it will move on its own. You don't need to impart it any velocity. Just if you create a smoke ring or you create a vortex ring, why does it translate? It translates because of the combination of the mechanism that I just described. So this is known as mutual induction. So you have the fact that there are vorticity vectors which are not parallel to each other. Each of these small segments of vorticity would contribute velocity on the other segment, and the net contribution is that that vortex ring is going to move, it is going to translate. And this is again, you can see it. This is not something which is a very abstract entity. You can get the mathematical answer of what is the self-induction velocity of a vortex ring, and you can then compare it with what you will get from experiments. That if you create a vortex ring, which is again not very hard to make, once you create a vortex ring, you see it will propagate. Obviously, eventually it is going to grow and then break up, all things will happen, but the initial stages when it is propagating, the speed of the ring can quite reasonably be approximated based on what you get from theories like this. So that is the idea of knowing about Biot-Savart and how you invert the velocity field, how you get the velocity field by inverting the vorticity field. And this is the point I was making, that this is a non-local relationship, because you can have vorticity only in few locations in the flow, but that is going to drive velocity everywhere. You can have vortex lines, so you can think of your flow being made up of few vortex lines, which means vorticity is only present at those locations where the lines are present. But then this is going to lead to a velocity field at all locations, which is why I said that studying vortex dynamics or studying using vorticity is a very economical way of studying fluid mechanics, if possible. If you are able to actually understand your problem purely through vorticity, you can reduce the amount of stuff that you need to study. So this was about the inversion process, but we go back to the picture of circulation. So we said that circulation is expressed in this manner, that I have a closed circuit and I want to write down what is my circulation. So what I will try to do, I will try to calculate the rate of change of this circulation following the fluid particle. So the point is the following. I have a circuit C. This circuit is made up of fluid particles everywhere, right? It's a material line. I am tracking this. So this line is going to do all kinds of things. My question is, how does circulation change as this circuit evolves? So, as I have measured, so I have measured the circulation at time t equals to 0 in this, I measured the circulation at time t equals to 0 when I mapped that circuit. What would happen if I basically keep tracking that circuit with time? And the claim I am going to make now is that the circulation is going to remain conserved. So, we will see how that arises. So, this is ddt of u, let us use the index notation ui dli. If I am doing a material derivative here, so dui dt dli plus ui ddt dli. So, there is a small line segment that we have, and if I now use my momentum equation here. So, momentum equation we have learnt that dui dt, rho dui dt is minus gradient of p plus some body force and there is some viscous forces in the problem. So, there are viscous forces, body forces and pressure gradient. So, if I consider the fluid to be inviscid, which means my equation becomes dui dt minus dou p dou xi plus FIB. And the body forces that we have in mind, we are going to consider conservative body force. So, conservative body force, and a classical example is that due to gravity. So, I can, for a conservative body force, I can write it as gradient of a potential. If it is gravity, then that potential is potential energy. So, the potential energy would basically give me the force due to gravity, the gradient of it. So, I am treating it as a conservative body force. So, let us maybe I'll just write it as rho gi and then write the body force. So, this is dui dt minus 1 by rho dou p dou xi plus gi, and gi I can write as minus dou xi of g x3, right. It is just saying that the Gz or Gx3 is basically the potential energy that I have per unit volume, and then when I take its gradient I get the acceleration g. So, the minus sign is because dou x3 of x3 would be 1 minus g pointing in the third positive direction, which is g is pointing down. So, that is how I have added this minus sign. So, the underlying point is that whatever you have here as the acceleration, you are saying that this body force or this acceleration that you have here is due to a conservative body force. So, here I can then write du dt as minus 1 by rho dou p dou xi, and I will have dou pi dou xi, where pi is minus minus g x3, whatever is the conservative body force that you have. dli. And here for the second term, I am going to write this as, I will take the material derivative inside, I will have ddt of that small line element and then the differential of that. So, what we have now is the rate of change of the circulation is minus 1 by rho dou p dou xi plus dou pi dou xi, which is basically a conservative body force, over that contour that I have, and then for the second piece I have ui d. Now, dli dt for that small line element. So, I have a small line element which I am integrating. This would just be the velocity. So, that small line element as it moves, that is going to be my velocity. So, I will get ui dui. So, I am integrating over a contour. I considered a small strip of that contour, and that contour is basically going to change in time due to the velocity at that particular location. So, the second term ui dui, I can write it as d of ui square by 2. So, this is a total differential. I am basically computing d of ui square over 2 over a closed contour. So, I come back, whatever may be the shape of the contour, I come back to my starting point. So, when I am basically going to evaluate ui square by 2 when I return back to the same point that I have started out from, which means if the function is obviously continuous. So, when I come back to the original point, the answer that I am going to get is same. So, it will be 0. So, this will go to 0. Dou pi dou xi dli, this would be the value of pi in the same spirit at the initial and the difference between the final and the initial location. So, I have a gradient of a potential, I integrate it over a curve. So, when I compute it, it would be the value of that potential at the final point minus the initial point. Now, the final and the initial point coincide is going to be 0. Now, this is not something that is very surprising, because the definition of a conservative body force would be there should not be any work done over a closed path. So, what we started out from g dot dl, that is basically the work done per unit mass. So, that should be 0 on a closed path, which is basically what we are saying here through a formal definition of a conservative body force. So, both these terms go to 0. So, we are left with one single thing, that in absence of any non-conservative effects, any viscous effects, I will have the rate of change of circulation will be given by the pressure gradient and density in the following form. Now, here up until this particular point, I did not say anything regarding the evolution of density. There was no comment being made regarding how density is actually evolving. It can be a constant density. So, rho can be constant, in which case I have minus 1 by rho dou p dou xi dli, and this will be 0, because it is a gradient evaluated over a closed contour. So, the final answer would be the value of pressure at the initial and difference between the initial and the final point, and if they coincide, it should be 0. What if rho was not a constant? So, if rho is not a constant, we will assume two forms. One is P equal to F rho, because if you say rho is not a constant, then we can't proceed any further. So, we have to assume some kind of dependence or some kind of relation or some kind of an evolution for rho. So, if you say P is a function of rho, then what I have here is 1 by rho d, that functional form f of rho dxi dli, and because it is now just a gradient of some function of rho by 1 by rho, I can write this as a gradient of some other function of rho. So, my starting point was 1 by rho dou p dou xi, I can't do any simplification, but if p was a function of rho, then I can write this as dou xi of some function of density, because pressure itself is a function of density. So, if pressure itself is a function of density, then this particular relation can be simplified to writing it as a gradient of some function of density. You can say, take some trivial example. So, trivial example would be if you say that pressure was proportional to density. If pressure was proportional to density, then this would basically become 1 by rho d rho dxi with some factor, which you can then write as dou xi of ln rho, right. The gradient of log rho is 1 by rho gradient of rho. So, you can define any functional form of density the moment you make this strong statement that pressure is purely a function of density and nothing else. So, when pressure is purely a function of density, then this integral can be expressed as a gradient of some quantity, and the moment you express it as some gradient, you are in business, because then this becomes 0. So, when you have P as a function of purely a function of density, then the circulation is conserved following a closed material loop. And fluids for which P is a function of rho, these are known as barotropic fluids. I mean, we know in general pressure can be a function of rho, temperature, if it is some system like sea water, then it can be a function of salinity, it can be a function of all these quantities. But if you consider the idealization where pressure is purely a function of density and no other variable, then this is a barotropic system, and when you have a barotropic fluid, then your circulation remains conserved. Obviously, a constant density is a very special case of a barotropic fluid. P as a function of rho, if rho is a constant, that is the trivial functional relationship that you have. P is equal to like some constant related to rho raised to the power 0. So, there is no dependence, that is the trivial relationship that you have. So, this is what is known as Kelvin's circulation theorem. It is a very useful statement which gives us that in a flow, regions of vorticity are not going to remain preserved in their shape, preserved in their form, right. It is going to, it will evolve. So, as I draw a contour here, the contour at a later time can take a very different shape. So, this is C prime, this is C. The two contours will not be the same, because they are going to deform, they are going to stretch, they are going to rotate. But what will remain conserved is the circulation that you are measuring in this. This is a very key idea. This is an important idea, that if your fluid is within the assumption of it being inviscid, there are no non-conservative forces acting on the system, and the system is also barotropic. So, inviscid conservative body forces and barotropic fluid. If you assume these, then circulation remains conserved, and that is a very powerful way of understanding what is going on, that you are not tracking vorticity, you are tracking the flux of vorticity. So, a lot of things will go on in the problem, but what you are looking at is the flux of vorticity. So, this was a description of what is going on regarding circulation, how circulation remains conserved. We also saw an expression for what is happening regarding obtaining velocity given, that is vorticity. But something that we have not done yet is what is the evolution of vorticity. How does vorticity evolve? So, we have our momentum equations, dou u dou t, u dot del u minus 1 by rho grad p plus some body force. So, I am ignoring viscous effects. And if I do not say anything about density being constant, then I have another equation for density, which is my equation of continuity, that is the following. So, these are the two equations that I have if I am considering my system to be inviscid. Now, if I take curl of the first equation, so curl of the first equation would be curl of dou u dou t, curl of u dot del u minus curl of 1 by rho grad p and curl of F, the body force part. Now, if F is conservative, going back to the same point, that if F is conservative, as it would be for things like gravity, then curl of F should be 0. That is restating the same point. For any conservative body force, it can be expressed as gradient of a potential, and thus the curl would be 0. So, there would be no contribution to the vorticity from the body force. Now, does this mean that there is going to be no contribution to vorticity from changes in density? We think of density variations associated with changes in body force, changes in buoyancy. Now, does that mean that I can have density changes and no contribution to vorticity in the problem? Because I see that del cross F is clearly going to be 0. So, that is where we will do a little bit of a simplification. So, u dot del u, again I am going to use vector calculus identities, some of these we have used in tensors earlier. This can be written as del of u square minus 2 minus u cross del cross u. You can verify these identities by expanding them using index notation, that u dot del u can be written as gradient of u square. U square is uj uj. So, gradient of u square by 2 minus u cross del cross u. Now, when you take a curl of this, what will happen to the first term? This should be 0. Curl of a gradient is always 0. So, we land up with the fact that the curl of the advective term, the advective nonlinearity, is curl of u cross omega. So, we now have the first term is curl of dou u dou t. So, commuting the two operators, I get dou omega dou t. The second term is curl of u dot del u, which is minus curl of u cross omega. So, if I expand minus u cross curl of u cross omega, I will get plus u cross del omega minus omega cross del u plus omega del dot u, and there will be one more term which is u del dot omega. So, if you do that full expansion. Now, this term is 0. I mean, for any vector A and B, curl of A cross B, you will have 4 terms. The last term is 0 because vorticity is always solenoidal. Vorticity is curl of a velocity field. So, by definition, vorticity will always be divergence free. So, this is always 0. But the second last term need not be 0 if the flow is not incompressible. This is divergence of u. The last one is 0 by definition because vorticity is curl of a velocity field. So, it will always be divergence free. But velocity is not always divergence free. It is divergence free if we say it is incompressible. So, now if you write your LHS, so the LHS is dou omega dou t plus u dot del omega minus omega dot del u plus omega del dot u. That is your left hand side. And your right hand side was minus curl of 1 by rho grad p. One by rho grad p is going to be 1 by rho square gradient rho cross gradient p. Sorry, this is the curl here. So, curl of 1 by rho gradient p would have a term that is gradient of 1 by rho curl or cross product with gradient of p plus 1 by rho curl of gradient p. This term is 0, this term survives. So, this term is going to be minus 1 by rho square gradient rho cross product with gradient p. So, we are done now with terms of the LHS and RHS terms. So, we have dou omega dou t plus u dot del omega is equal to omega dot, I am taking that to the right hand side now, omega dot del u, omega del dot u plus 1 by rho square del rho cross del p. This equation is valid as long as the flow is just inviscid and has only conservative body force. There is nowhere I am using anything to do with incompressibility. So, you have an evolution of vorticity. If you look at the left hand side, this is the material derivative of vorticity. LHS is the material derivative of vorticity. It is telling us how vorticity evolves in a flow. And there are 3 terms here, 1, 2 and 3. The last term is something that is quite interesting. There is a source of vorticity that is coming in from gradients of density. The last term is of the form 1 by rho square gradient rho cross gradient p. Now, if rho is constant, this is trivially 0. If there is no density variation, then this is trivially 0. If we go back to our knowledge of barotropic fluid, so if I have a barotropic fluid, if P is a function of rho, then 1 by rho square grad p, grad rho cross grad p will be 1 by rho square grad rho cross grad rho into f dash rho. If pressure is a function of density, then gradient of pressure will be along gradient of density times some derivative of that functional form. Now, grad rho cross grad rho is 0. A cross A is 0, they are parallel to each other. So, when you have a barotropic fluid, this term again becomes 0, which introduces us to a new terminology, that is a scenario where you have a baroclinic fluid where lines of constant pressure, which are isobars, and lines of constant density, which are known as isopycnal lines, they do not coincide. They are not parallel to each other. So, when there is a misalignment of lines of constant density and constant pressure in a fluid, you are going to create vorticity. So, if the fluid was barotropic or constant density, this would be 0 if you have a barotropic fluid, or this source of vorticity is known as the baroclinic generation or the baroclinic torque acting in the fluid. If you have density variations, you can generate vorticity, but you need to have misalignment of pressure contours with density contours. The second term is obviously 0 if you have incompressible flow. But the first term is something that is quite new, omega dot del u. So, this is something which we will see in our next lecture, that what is the significance of this particular term. So, this equation in its entire form is sometimes known as Friedman's equation, and if you were to not have the baroclinic term, so without the baroclinic term, it is known as Helmholtz equation. So, it is an equation for the evolution of vorticity that is driven by these three additional terms on the right hand side. There is a baroclinic torque, there is a term that comes from the divergence of the velocity field, and then there is a term which comes in from a slightly different kind of a combination, which is omega dot del u, and this is going to be a term that we will focus on, and it is a very important term in terms of how vorticity evolves in strongly turbulent flows. So, we will stop here.